Crossing the Channel underground has been an engineering dream since 1802. However, this dream faced two main challenges: politics and the intense hydrostatic pressure of the English Channel. The tunnel needed to withstand the weight of the sea and navigate complex, waterlogged fault lines. A critical step was finding the right geological layer. Engineers had to avoid highly permeable or unstable ground. Extensive surveys identified the Chalk Marl, known as the Goldilocks zone, as the ideal, practically impermeable and stable corridor for the tunnel. The tunnel boring machine, or TBM, acted like a robotic caterpillar. It simultaneously excavated rock, removed the debris, and assembled pre-cast concrete rings to line the tunnel. The machine pushed off the placed rings to move forward, inch by inch. The project required 11 massive TBMs in total, 6 starting from the UK and 5 from France. Since the machines were too large to transport whole, they were shipped in pieces and assembled in large subterranean assembly caverns before they could begin tunneling. GPS does not work underground. To ensure the French and British tunnels would meet, engineers created a unified coordinate grid. They used electronic distance measurement on the surface to map a web of triangles, and then transferred those coordinates down the shaft using optical plumb lines. Once underground, the TBMs used a precise laser system for navigation. A laser theodolite mounted behind the machine targeted a photosensitive target on the moving TBM. A computer instantly flagged any steering error, ensuring the tunnel remained on the quote tunnel axis. A small service tunnel was dug ahead of the two main tunnels for two reasons. First, it acted as a probe to confirm ground conditions. Second, if weak rock was encountered, engineers could inject grout to consolidate and strengthen the ground for the main TBMs. On October 30th, 1990, a small probe was drilled from the UK side, confirming the alignment. A few weeks later, on December 1st, 1990, British and French workers made a historic handshake through the remaining rock, creating the first dry land connection since the last ice age. A high-speed train in a tight tunnel acts like a piston, compressing the air in front of it and creating massive resistance. Engineers solved this by including piston relief ducts, which allow compressed air to escape to the adjacent tunnel, neutralizing the pressure effect. Trains generate significant heat through air friction, which accumulates in the confined tunnel. To maintain a safe ambient temperature of 25 degrees Celsius, a network of pipes carrying chilled water runs the length of the tunnel, continuously absorbing the heat. The tunnel is a modular system, not just a single tube. Massive crossover caverns allow traffic to be diverted to the other tunnel if a train breaks down. The central service tunnel acts as a pressurized escape route, pushing smoke away from evacuating passengers in case of fire. After the job was done, the French dismantled and removed their TBMs. The British TBMs, however, could not reverse and were too costly to dismantle. The solution was TBM burial. The machines were steered downward, driven into the rock, and entombed beneath the track. The final tunnel spans 50.5 kilometers, with 38 kilometers under the sea, reaching an average depth of 45 meters below the seabed. By conquering the forces of the sea and mastering extreme precision, engineers proved that even the English Channel could be defeated.